Alrighty, welcome back to operating systems. Today, fun lecture. So this will prepare you for Lab 5, and we are going to run the world's greatest bank ever created. So this whole example, I will be relying on you. We will try and make the best bank. We will make issues, and the more mistakes we make, the more we shall learn. So how this is going to be set up is we are a bank, a successful bank. We are going to simulate doing 10 million transfers between our happy customers. So I have a simulation that can vary the number of customers we have, and we'll simulate doing 10 million transfers. So how this is going to work is each account has a unique identifier associated with it, and then a balance. Let's just assume, for argument's sake, that they each start with $1,000. So we are just going to simulate transferring between all of these different customers. So we just generate transfers between random accounts. And how this is going to work is they're going to just transfer 10% of their current balance to the other account. So if we are a successful bank, we should have the same amount of money. Our customers are just moving money around. We should always have the same amount of money. So the only other part of this is they must call this securely connect to bank before starting a transfer. So other than that, it's done live. We'll have data races, we'll have deadlocks. Hopefully we will have a whole bunch of fun. Our goal is mostly performance. We want this thing to run a whole hell of a lot faster than initially without using threads or anything like that. And initially it will take about 10 seconds. So it's just this bank sim program, and we can specify the number of accounts to create. So let's look at that for a second. So up here I have a few defines. So I have my starting balance is $1,000, number of transfers is 10,000, and then, well, we're going to hopefully speed it up using threads. Eventually we'll use 8 threads. And then I have a struct account that represents an account. So each account has a identifier and then a balance. So we don't let them go negative or anything like that. So it's just an unsigned int to keep track of their money. Then I just have, a static number of accounts that we specify on the command line, and then a big array of all these accounts. And then I have the securely connect to bank, which just simulates, securely connecting to a bank. Hopefully we can parallelize that. The main thing we want to make sure we run in parallel is this transfer. So transfer securely connects to the bank, and then transfers 10% of the balance from the from account. So transferring between 2 accounts. So from, so when we're taking money out of, so we're taking 10% of its balance out, subtracting that amount from that account, and then transferring it to the other account. So we subtract from one, add to the other. We should have the same amount of money at the end of the day. Then I have this placeholder for a function to run for my threads that we will add to. Then check error, and then other than that, we can ignore. It just initializes things. And then here, this is what we want to parallelize. So this is simulating doing the transfers. So this will do 1 for every account. So one for every transfer. So this runs 10 million times. Picks a random account to get a from index to. So it uses rand. Then toIndex picks a random account, and then the account it uses, well, just indexes into that big accounts array and then takes the address of it, so we have a pointer to a struct. So everyone okay with that? So if we calculate our initial funds, so every account starts with, $1,000. If I have 10 accounts, how much money is this bank managing? $10,000, right? So if I do a whole bunch of transfers between different accounts, at the end of the day, how much money should be in the bank? 10,000, right? So that will be our sanity check. So let's run this program. So here I'm going to just use user bin time to keep track of how long this program runs for. -p will just present like lines in a different order to make it a bit more readable. And then I'll run my bank sim with 10 accounts. So initially I have $10,000. I also keep track of the memory used. So in this case, we don't use that much. It's just 0 megabytes. And then after we do all the transfers, we have $10,000. The real time, that's wall clock time, so it took like 10 seconds. User time, how much time spent in user mode, and then sys is how much time spent doing system calls. So now, if we want to make this faster, what shall I do? Parallelize it, right? I have threads. So I wrote a whole bunch of starter code here. So here, this will create, in this case, 8 threads, creates a thread ID, mallocs it so that there's no data races or anything like that. I'm not giving an address to a stack or anything like that. And then we'll pthread create it. So I also need to uncomment. Threads. Did I miss a line? Okay, well, I need to initialize my pthreads. So pthread t, and then I call it threads, and it is num threads. So I'm creating a big array of 8 threads, create all of them, tell them to run this run routine, give it the thread ID, and then hopefully it frees it. So I set all my 8 threads off, then join them all so they should all complete. And then after that, I will go ahead and check the final balance. So this is what I'm trying to parallelize. So if I just put this here, is that good? I made my program 8 times faster? No. What should I do here? So, well, let's run it and let's see if we sped it up. So we run this. Oh no. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Shoot, shoot, shoot. Okay, we made it slower. What's my problem? What am I doing here? Yeah.
Are we just doing it like 8 times more?
Yeah, so now I'm doing like 8 times more work, right? So each thread is doing 10 million transfers. If I have 8 threads, they can all do 1/8 of the work, right? So I still want to do my 10 million transfers. So first thing, I should just take this and divide it by the number of threads. And I just assume that this divides nice and equally. So now each thread does 1/8 of the work, right? So ideally, this makes it go 8 times faster, right? So everyone agree with that, 8 times faster? So let's run it. 1, 2, 3, 4, 5, 6, 7. So didn't quite go 8 times faster. Went 7. And our final balance, hey, we made $33 million. Sweet. What are my issues here? Yeah, I have data races. Is it what you're going to say up there? Okay, so first issue is I have a lot of data races, but you would think, just looking at this, it should go 8 times faster even if it's wrong, right? I'm not waiting on any other thread. They're all just going. So turns out this is where we have to look up things. So if we are observant, this thread run function calls rand. Well, is rand thread safe? Well, so you might think, hey, maybe it is or isn't thread safe, so we can just look at the man pages for rand, look at the attributes, and it says, oh, it is thread safe. So if it's thread safe, that means there's no data races from using rand, as opposed to, just using them in every thread. But if there's no data races using rand, that means it probably uses a mutex. And that means it's probably slow. So that's why we didn't quite get 8 times speed up, because, well, there's some shared state in there. If it's safe, doesn't have data races, it has a mutex. So turns out there's a rand_r function, and what rand_r function is, it doesn't rely on any external state. We have to give it some state, but then it will be, really fast because it doesn't depend on anything else. It doesn't need any locks or anything like that. So I'll save you some time. If we look at rand_r needs you to give it a state, which basically you need to give it a starting seed. So we can go ahead and make it faster by, I will just declare a variable called unsigned int seed, make it equal to the thread ID initially, and then here I will change rand to instead use rand_r, and then you give it the seed. So in this case, it's also thread safe, but now there's no shared state between threads, so if I do this, it will likely be faster, and aside from performance reasons, and actually doing this in practice, you wouldn't be expected to do this. This is to just show you. So now if I do it, my bank, hella fast now, right? So now I'm about 8 times as fast. Holy crap, I'm rich. So yeah, data races happened. So just looking at the output, every time we run it, it's really obvious in this case if we have our sanity check, right? But what if I was, I don't know, some unnamed bank, and I had, 10,000 accounts, so I was managing lots and lots of money. So if I'm managing $10 million, that's not too bad, right? What about if I was an even more successful bank and I was managing, I don't know, $1 billion? So, yeah, I made $100 or I'm a bit less. What about if I was managing $10 billion? I lost a little bit of money. Okay, what about if I managed $100 billion? Hey, no data races. Why is this happening? Yeah.
Number of transactions is the same, but the number of accounts increased.
Yeah, so number of transactions is the same, but if I have more accounts, it's less likely I have a data race, right? I'm just picking 2 random accounts, transferring. If I have a lot, I'm less likely to see the issue. So this is kind of, I don't know, counterintuitive to other programs you've written, where the more data you have, the more it looks like it looks correct. So smaller programs will show the issue a lot faster than larger programs because you're more likely to actually see the data race. So this is the case where you can be essentially too big to fail, right? So you write this crappy code, it goes 8 times faster. If you're managing, I don't know, some huge bank, you have a lot of customers, you never see the data race. You might blissfully think that you just made things 8 times faster. You can collect your big paycheck and go home, everything works. So issue is data races. So let's go back to just 10 accounts where, yeah, bad things happen. So how do I fix this? Yeah.
Maybe have a lock for each account.
Have a lock for each account. Okay, so that's a good idea. So yeah, our first thing might be here is where we have our data races, right, between the two accounts here. So naive solution that will get rid of the data races just to put a lock around, you know, this whole thing, both transfers. That's going to be slow because essentially I'm, you know, serializing it. It won't be too bad because I assume this securely connected bank can run in parallel, so we might get a little bit of a speed up, but probably not much. So we might figure, hey, maybe I need a mutex for each account. So let's create a mutex for each account. pthread mutex t. I'm going to be creative and just call it mutex. So good, every thread now has a mutex, or every account now has a mutex. So what would you like me to do with said mutex?
You gotta acquire it for the account you're transferring from and to.
So I have to lock it, pthread mutex lock. So in the thread I'm going from, that is from's mutex, and then address of, because I need its address. So you want me to lock the from, and then what?
Lock 2 as well, make the transaction, then unlock both.
Lock 2. And then unlock both where?
After line 55.
After line 55. So let's make it nice looking. Everyone agree? Any arguments? Should work? Oh, we have one argument, one dissenter. Will it not cause a deadlock? Ooh. Yeah.
Yeah, one of the from of one transfer is equal to the two of another, and they can deadlock each other.
Yeah, so we could easily get into a deadlock situation here. Let's just, you know, we can run it again. Make sure here, 1, 2, 3, 4, 5, 6, 7, 8, 9, crap, probably deadlocked. I can double check. If I'm deadlocked, I can go to htop, see all my CPU cores are doing nothing. So probably indicates a deadlock there. So nothing's going on. Oh, that's fine. Okay, so we deadlocked. And why? Well, we could have thread 1 that transferred where from is like account A and 2 is account B, and then thread 2 where from is account B and 2 is account A. And in that case, we might have a deadlock where thread 1, right, would acquire lock A first, right? Acquire lock A first, and then thread 2 could acquire lock B, and now each thread is waiting on each other's lock, and they deadlock, right? So everyone get that deadlock? Fix it. What do I do if I want to avoid this deadlock? Yeah.
And then maybe like lock it one at a time, like do lock of the from, and then unlock it before we lock the
So unlock it before we lock the 2. So you want something like this?
No, I mean like just after the like we can have the unlock maybe before line 58.
Unlock before line 58.
Yeah, and then have the lock of 2 after we unlock from.
This?
Yeah, and then also maybe move the 2 after, like after, yeah, like after the yeah.
This? So, I mean, we can try this. So this works. It has a subtle issue though. So the subtle issue is if we compare it to running sequentially, where like we have, essentially we have transactions, the balance in any one account might be off. So I won't get into the details why exactly, just it's very subtle. It's because we're doing it as like a big transaction. So any individual account might have the wrong balance. But in this case, if you're the bank, who cares about the customer? So the customer can have the wrong balance. I'm not losing money anymore. So you might get your raise here, but they might have increased customer complaints to the call center. So can't do that. So let's rewind. So yeah.
So only lock the second one if you can acquire, or like you need to make sure you account lock both. So if you can't acquire the second one, you should release the first one.
So
With a try lock.
I should do a tri-lock? So yeah, we can do the tri-lock solution first. So remember, in order to break a deadlock, 4 necessary conditions, only 2 we can really do anything about. Break circular wait by always acquiring the locks in the same order. Or the second one is we can break, hold, and wait. So you want break, hold, and wait. So to break, hold, and wait, that's where we need our tri-lock. So we could do while, so pthread tri-lock, whoops. So we could try and get the 2 lock, whoops. So we'll try, and in this case, again, tri-lock will return 0 if it successfully locked it and return not 0 otherwise. So if it's not 0, then what do we want to do in the while loop? We probably want to unlock the from, right? So what else do we want to do? So we unlock the from, then what? That's it? We're good? Yeah. Lock it again? Oops. So we'll just lock it after again. That's it? Yeah. Wait a bit? Yeah, maybe I should wait a bit here. So we could wait, we could yield, we could do whatever. The Linux way to yield, there is a system call for that. It has a very generic name. It's called schedge yield. So that will yield, if you're a thread or a process, it's just a very generic name. That's basically what yield is. So yeah, we could, so in this case, we try to get the from mutex, try to get the 2. If we did not get the 2, then we will unlock the from, yield, so we don't have any locks when we yield. Then we lock the from again and then try and get the 2 again. So if tri-lock is successful, that means I've acquired the mutex, and that means I don't need this line. So so this looks good. Someone's beeping. So perfectly good thing to do. Okay. So, anyone want to stake their raise on this working? So, do we want to be a big bank or a small bank? So, if we are a big bank, too big. Okay, if we're a slightly smaller bank, one, 2, 3, 4, 5, 6, 7, 8. Oh no. Oh no. Oh no, we're going to get fired. Let's see. So, yikes. It looks like, it appears to be deadlocked, but my computer's heating up right now. So all of those 8 cores, so there's like 10 on my machine, but we just used 8. And they're all really unhappy right now. So that might give us some evidence as to what is going on. So let's close this before VS Code crashes again. What's going on here? Anyone see the subtle mistake we have? As I will tell you, we have the right idea, but there's one strange issue that is causing it to constantly, no matter what, even on a single thread, constantly go through this loop over and over and over and over and over and over again. What do you want me to try? Isn't programming fun? Yeah.
Maybe you shouldn't yield.
I shouldn't yield. All right. That's one try. Screw yielding. I don't like other threads. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope. So yield didn't really matter. Yeah.
So if you are able to try log, like but you can actually log it, I don't know if try log actually logs it.
Yeah, try lock will actually lock it. So we probably always get stuck at least once. Let's see. 1, 2, 3. Yeah, it's probably stuck. How far can I push it before I run out of memory? 1 more 0? Hey, yay! Does that give us some evidence? So I guess you get your raise back if you're at a large enough company that doesn't cause VS Studio to run out of memory. What else should I try, or any ideas of where we went wrong? Yeah.
Could it be that you are unlocking from first and unlocking to second?
So,
Whereas you're also locking from first and locking to.
so here it's not being caused by a real deadlock. So whenever I yield, right, it doesn't matter if I acquire to first or from first, because if I get one and I don't get the other, I give up the first one. So in this case, whenever I yield, I don't have any locks, so I don't have any deadlocks, no problem. Yeah?
I guess from and to could be the same account. So you are looking at the same.
Yeah, ooh. What if from and to are the same account? So if from and to are the same account, well then that's the same mutex, so it would be the same mutex, so I would lock it, and then try and get my own mutex, which will fail every single time. So, subtle thing. So this, you might think, in my application, transferring to and from the same account, does that make any sense? No, not really. So if I wanted to be clever, right, they're given by pointer, so if the pointer to from is the same as the pointer to, that means it's the same account. So that means, well, I can be fast, I don't have to do anything, right? So now I shouldn't have a deadlock, because that time I was like deadlocking with myself, right? Who wants to stake their raise on this one? So we're not deadlocking ourselves, and if we eliminate hold and wait, we won't have any deadlocks, right? So if I wasn't lying to you, this should work. So let's make sure. So if we're the big bank, runs real fast, gets the right answer. So that's good. No deadlocks, no data races. What if we're the small bank where bad things may happen? So if we are the small bank, let's see if this works. Yes, it does. So it will be a bit slower because, well, it's more likely that two accounts interfere with each other, so there's more contention for the locks because there's less accounts, only 10 accounts, so it'll go a little bit slower, but we don't have any data races and we don't have any deadlocks, so we will always complete, we will always have the same amount. So it'll probably speed up a bunch, even if we have 100 accounts. We get like almost the 8 times speed up we don't have any data races, we don't have any issues or anything like that. Cool, huh? Anyone disagree with our cool bank? Ready to go get paid? So, what about if I was like, hey, I don't want you to break, hold, and wait. I want you to not have a deadlock some other way. So, what's another way to prevent a deadlock here? So let's go back. So, yeah.
Maybe, okay, you compare the pointers, and then you always acquire the one with the smaller address first.
Yeah, so another way to avoid a deadlock is, well, if I always acquire the locks in the same order, I won't have a deadlock. I could look at the account, like use their memory addresses to compare. Turns out each account has a unique ID. I could use that too. Maybe it might be a bit clearer. So in order to do that, what I might do is, well, I'll pick which lock to lock first based off whatever has the lowest ID. So maybe I here create a temporary mutex, or just create a pointer to a mutex called M1. That will be the first one I lock, and then M2, which will be the second one I lock. Let's move this after this. So in that case, I have to pick which I'm going to lock first and which I'm going to lock second. So I could check like, hey, is the from accounts ID less than the to accounts ID? In that case, then M1 should be the from account mutex, and then M2 should be the to accounts mutex. Otherwise, if it's the other way around, then I just reverse them, right? So I do this. M1 is the to, M2 is from, and then I always acquire them in that order. So here I would lock M1, then M2, and then here, doesn't really matter. Just for pretty sake, I'll unlock M2 and then M1. So, should this prevent a deadlock? Hopefully, right? I always acquire the locks in the same order. My problem before where I deadlocked if I was transferring A to B and B to A, well, now if it happens, let's assume A has a lower ID than B, then in that case, M1 would be A's lock, M2 would be B's lock, and in the other thread that's transferring B to A, well, the from account, which would be B, is greater than to's account, which is A, so M1 in both cases would be A, and M2 would be B. So I would always acquire A then B, no matter what from and to is, right? So, turns out this is another way to prevent a deadlock that works perfectly well. So, if I run this, boom, no problem. You can pick whatever you want. So, everyone okay with that? All right, any other questions or any other things we want to do improperly. It was kind of sweet when we made like $17 trillion, wasn't it? Although you would probably be responsible for that and then you'd probably go bankrupt, but that's when you hope for a government bailout. All right, anything else? Otherwise, we can wrap it up. It was just doing this example today. We have made the world's most successful bank. So, yeah.
Just wondering, what is the connection between this to the lab? Like, what's the difference in the similarity?
So, like lab 5, I'm basically giving you a hash table and then telling you, and then parallelizing it, and then telling you to make it safe. So basically, you'd be given this code and have to create your own mutexes and do your locks and unlocks, so you don't have any data races and you don't have any deadlocks, and you have to go faster. All right, cool. Then we can leave early. Congratulations.